So our last problem here in chapter 8 kind of looks at ranking ions by size. And we're going to, think very similarly to how we thought about sample problem 8.3, where we ranked elements or atoms by size. But now we're going to think about what changes when all of a sudden we become ions. And one of the things to think about is the fact that when we become positively charged, that means we have a greater number of protons than electrons. And that's going to allow us to hold those other electrons that are still remaining much closer and much tighter. So trends is when we become a cation. So cation formation, we become smaller than the parent atom. And the opposite is true for anion formation. So anion formation means that we become larger than our parent atom. When we take on more electrons, we give those electrons kind of more strength to kind of pull away from the positively charged nucleus because they're repelling one another. And so anions become larger in size. And so if we keep that trend in mind, that's going to allow us to kind of think about what we see here. But we're going to see some of the same trends that we saw just simply with atomic size, where changing the row that we're in is going to have some significant consequences. So again, we're going to treat this problem very much the same way that we treated our other problems. And so we want to make sure we have a periodic table handy. That's always going to be, especially with this chapter and periodic trends, one of your best cheat sheets. So again, now we're looking at calcium 2+, strontium 2+, and magnesium 2+. So like we saw with other things, what we have here is we have 3 elements that are present in the same group or the same column of the periodic table. So again, this is going to be the same group, which again is a column on our periodic table. And we're basically going to use the same trends that we thought about purely for elemental or atomic size, is that size increases as you go down. So again, the trends that we saw for that is you increase in size as you go from right to left, but you also increase as you go down, and that's going to be, again, the most significant effect that we see here. So in this case, our largest ion is going to be the strontium cation. This asks us to rank them in order of decreasing size, so we need to put our largest first. So strontium is going to come first, and then calcium, and then magnesium. So that one's pretty straightforward, again, an apples to apples comparison. Looking at potassium cation. So potassium cation means we are isoelectronic with argon. Sulfide anion and chloride anion. Sulfide anion gaining 2 electrons, chlorine becoming chloride and gaining 1 electron. All 3 of these species are isoelectronic. So again, all 3 of these are isoelectronic. So whether we're talking about K+, S2- or Cl-, they all have the same electron configuration as argon. So the question becomes then, how do we differentiate what's different here? And the idea is we need to think about the ratio of electrons to protons. And as this ratio becomes greater than 1, again, we get larger, and that's going to again happen when we become an anion. As this ratio becomes less than 1, we become smaller. So in this case, the largest species is going to be our divalent anion, followed by our monovalent anion. And then lastly, even though this was a species that was 1 down on the periodic table, we showed this here, potassium was in N=4, with the other 2 were N=3. As soon as we lose that 4s electron, it bumps us down that these are all the same. They have the same number of electrons. So what must be different then, again, is this ratio of electrons to protons, which determines how tightly those electrons are held to the nucleus, which is ultimately what determines size. All right, last species here. Again, looking at Au3+ versus Au+. Again, we're going to kind of apply our same principle here that as we increase the positive charge, meaning we're decreasing the number of electrons, we become smaller. So again, we're going to see that the +1 gold cation is going to be larger than the 3+ cation because there are fewer electrons in the 3+ cation, and so the electrons that are remaining are held much more closely to the nucleus, and so that species is smaller.